Welcome. In this video, we will be taking a look at 2.2, looking at continuity and algebraic limits. This is the third lecture in the brief calculus series. So let's start with a definition of what continuous means, or what it means to be a continuous function at a point. So definition says a function f is continuous at x equals a if and only if three things here are true. So the first thing is the limit as x goes to a of f of x exists. So the two-sided limit must exist. F of a is defined, that's number 2. The functional value is defined. And then number 3, the two-sided limit, the limit as x goes to a of f of x, is equal to the functional value at f of a. So those three things have to be true for a function to be continuous at a singular point, x equals a. So below here we have three graphs that specifically take a look at this idea of continuity. So the first function on the left is where we have a continuous function over its whole domain. There's no gaps or holes or jumps in the graph, and so we'd say this function is continuous. The middle graph will have a hole or jump point discontinuity in the graph, and so we see where this little hole pops up and it's not part of the continuous line. It's defined somewhere else other than where, again, that limit value would be expected to be. We would say that the functional value of here, the point of 1, is equal to 1, but the limit value, if we said the limit as x approaches 1 of f of x, we would call that equal to, looks like, -1. So we would say that the limit value at x equals 1 and the functional value at 1 are two different values. And then the final result, the break discontinuity, we have two sections of our graph that kind of break apart from each other here at the value of -1. So here we would say that the limit in this case, as x goes to -1, of the function f of x does not exist. So we see that these two discontinuous graphs, the second one in the middle and the third one on the right, actually violate one of these three principles. The middle graph violates the third principle here, that the functional value at the point and the limit value have to be the same. That's not true here in the middle picture. And then if I consider the third picture, well, the limit here doesn't exist on that break discontinuity graph. So just as some results here, again, the continuous graph or the function will have no breaks, holes, or jumps anywhere on the function. In other words, we can draw that function with a continuous line without picking up our pencil. If we ever have hole discontinuities, that would mean that the functional value and the limit value at the point do not agree. And then break discontinuities would be any time where our one-sided limits from both the left and the right do not agree. Another concept regarding continuity would be the idea of singularity points. So let's consider the definition for a singularity point, and then we'll take a look at two types. So a function not defined at an isolated point is said to have a singularity at that point. Singularities may be classified as removable or non-removable. So we'll take a look at both of these cases. First, the removable discontinuity. And we'll have a graph to kind of highlight the difference here. A function has a removable discontinuity if the function may be made continuous at x equals a by properly defining f of a. A hole in the graph is usually going to be a removable discontinuity. So if we considered this graph on the right, we notice that we just have simply just a hole in the graph where the limit as x approaches 2 does exist. Looks like we're approaching this height of 12 on our function from both ends, the left and the right, but there happens to just be an undefined point right there. And so one way we can consider this is if I consider the input x equals 2, currently the limit does not exist at the point 2, but we can define a point here, f of 2 equal to 12. In other words, I can choose this f of 2 to be defined at 12, and that would consider really defining a point there with that open circle, and that would actually close the gap between those two portions of the function. So now if I define that value and place it in the graph, I would have a continuous function. So this would be an example of, again, a removable discontinuity, or a removable singularity in this case, excuse me, a removable singularity. The second type looks a little bit different, where we can't actually make the function continuous regardless of what we do. So a function has a non-removable singularity if the function may not be made continuous by properly defining f of a. A break in a graph is usually an essential singularity. So non-removable or essential singularity would be the same types of ideas. So if we considered, in this case, looks like we are undefined at 0. So f of 0 is right now undefined. And regardless of where I choose to define f of a, if I was to go ahead and choose, just like my last problem, to define f of 0 at some point, regardless of where I put that point, either at 1 or at 0 or at -1, regardless of where I put that point, I'm still not going to be continuous. There's no way to force that function to be continuous over that point x equals 0. And so we'd say this is a non-removable or an essential singularity. There's no way to change that by augmenting my graph with a point. In the next few questions, we're going to be taking a look at some sketches of some descriptions of graphs. And this is going to work on kind of our skills of interpreting a statement and considering kind of what shape they might be describing in terms of continuity, the limits, and the functional values at a given point. So let's take a look at number 1. The function is continuous on the interval 0 to 10. We just want to find a function f of x where it's simply just continuous over the interval 0 to 10. So to do this, let's go ahead and just draw a little graph to start. If I wanted to have a continuous function over this interval, well, one thing I could do here is just be defined at 0. And it doesn't necessarily matter where. And I want to also be defined over the whole interval until I reach some point x equals 10. So over this interval, notice, from 0 to 10, I would be a continuous function. Again, it doesn't matter really what type of function we have as long as it's continuous with no breaks or holes in the graph. So that would be a continuous function over the interval 0 to 10. Let's take a look at a second example. We'll draw a little graph as well. So the function f of x is defined at x equals c, but the limit as x approaches c of f of x does not exist. So here we know we're defined at some point c, so let's mark some point c on our x-axis. We'll call this c. And we know the functional value exists, so we have some functional value somewhere on the graph defined at x equals c, but the limit does not exist. So one way we can represent this would be some function that breaks at x equals c, and where our left and our right-sided limit do not agree. And so the two-sided limit at x equals c would not exist. Now again, you can draw this a number of different ways with your lines, but we do want some sort of a break where the limit here does not exist. So that would be one example there. And if we wanted to augment this, we could say that here this is our functional value at c. We don't necessarily know what that is, but that height there would be our functional value. Taking a look at the third graph, we will have, we want the function f of x. The function f of x is not defined at x equals c, but the limit as x approaches c of f of x does exist, and that is equal to L. So here our limit exists, but our functional value is not defined. So it's kind of the opposite. So let's consider what that would look like. Again, we'll kind of just do a little sketch to start off with. And one way we can describe this is at a point, again, C, we are not defined, so maybe we could draw an open circle. We're undefined there. It doesn't matter what the height is, but we do have a limit that exists at L, and so we can represent some sort of a function that does meet at this value, and that height here happens to be L, because that's the limit as x approaches c. So in this case, we have what we'd say is the removable discontinuity. Or a removable singularity here. There we go. So we do have an undefined point at C, but we could define it at that value L if we wanted to make it continuous. Taking a look at the next one, number 4, we'll look at another example for a graph. The function f of x is not defined at x equals c, and the limit as x approaches c of f of x is equal to infinity. So here's another combination we could consider. Again, let's draw a graph to start, x and y axis. Let's start with maybe defining where our value c is. So let's say that x equals c. We know this is undefined, but we know the limit exists at infinity. So that would mean we have kind of both sides, the left and right side, we are approaching infinity. And so in a way, we can consider this as maybe a asymptote, undefined value at c. And then our function, we could say, is approaching that infinity value from both the left and the right. So something to this nature, where we have our function increasing without bound on the left and the right side of this input c. This would show that we have a limit going towards infinity, but we actually aren't going to be defined at the value x equals c. Last but not least, let's take a look at one final example. Number 5 says that we have a function f of x is defined at x equals c, and the limit as x goes to c is going to be L, but the function is not continuous at x equals c. So we're not continuous, so we're violating one of our rules, but we do have a defined value at x equals c, and we do have a limit. So this would be graphed in such a way that we don't violate the first two principles, but we do violate the last, that our functional value and our limit are not the same. So one way we could write this is with one open circle at a value c. So there is our limit that exists, and our functional value does exist somewhere else. Let's just maybe place it right above. But the limit value, we can call L right over here, is not the same value as the functional value we'll call f of c. So our f of c is at a different place than the limit value L. We're defined at f of c, and we have a limit that exists at L. So that would be kind of our jump point discontinuity. So let's consider kind of this removable discontinuity or removable singularity value a little bit more. So next example, we'll take a look at given f of x is equal to x divided by 3x squared minus x, determine what, if any, value to assign to the function to make it continuous at x equals 0. So first off, let's just double check of kind of what is happening at 0 and see what we can do to mediate that. So we have an input of 0 would be 0 in our numerator, and then we'll have 3 times 0 squared minus 0. So I think we're going to get just a value of 0 over 0, which in fact is undefined. So we are kind of out of luck. We do have something odd going on at this value x equals 0. So let's see if we can actually go ahead and find a value to define at x equals 0 so that we're going to be continuous. One way we can do this is to consider the limit as x approaches 0 and see if we're approaching a common value from the left and the right. So let's consider that now with the limit. We have the limit as x approaches 0. Excuse me. Turn this around. The limit as x approaches 0 of f of x, which happens to be our function x, over 3x squared minus x. And here we're actually going to introduce kind of an algebraic technique through factoring. So if I wanted to actually take this limit algebraically, as I have it set up here, one technique we could take is to take the limit and consider factoring the function that we already have. So this would be x in the numerator, and then we could pull out a common x in the denominator, making it 3x minus 1. So we do have a factored form here. And here in the limit, we're actually able to cancel those x values. The limit value is going to be the same regardless if we keep that factor or not. So we can continue simplifying this and say, let's cancel out each of those x terms. And we can rewrite our limit as the following. The limit as x goes to 0 of 1 over 3x minus 1. And now we'll notice that we actually can evaluate this limit at x equals 0. There's nothing odd going in the denominator, and so we can say that's 1 over 3 times 0, and then minus 1. And this would simplify down to just negative 1. So here we can actually assign the value of f of 0 to be negative 1. If I assign that value, this function now will be continuous at x equals 0. If I consider the second example in this section, we have a new function, x squared minus 3x divided by x plus 4. And again, we would notice that f of negative 4, if we look at that denominator, will have a denominator equal to 0 when we evaluate at negative 4. So this is, again, undefined. But unfortunately, when I consider taking a look at this function in a limit, so the limit as x goes to negative 4 here, of our function, this function actually does not have the capability to factor and simplify. If I try factoring here, you can again take the limit as x goes to negative 4. The numerator, we can take out an x term to leave x minus 3, and then x plus 4. But we'll notice that that doesn't necessarily do us a whole lot of good. There's nothing to cancel here. And so this limit here, based on what we see, this actually is indicating that this limit does not exist. It's still going to be undefined. There's no way to make that function defined at negative 4. And so here, this would be an example of an essential singularity. And so we could not make that function defined there. So we cannot assign a value here to make that function continuous at x equals negative 4. All right, let's take a look. Before we go into any more kind of direct algebraic limits, we'll take a peek at a piecewise function and consider the following problem. So we want to find the value of a, this is a constant a in our function, such that f of x is continuous. Okay, so we would like to go ahead and find where our function is going to be continuous. So it looks like we have kind of two separate functions that were defined as over two different domains. One domain is x is less than or equal to 3. We're defined as 4ax, and then over the second portion of our domain, x is greater than 3, we're defined by a quadratic function, 2x squared plus 3. So if we would like to be continuous at this point of 3, this is the only point that we would have issue with, is where we actually split our function. I'm going to try to consider, well, the limit and the functional value, I'd like to have those be the same thing. If we have the limit existing and the functional value at 3 existing, and they're the same thing, we then can know that we're continuous. So let's consider first the right-sided limit. Or excuse me, we'll do the left-sided limit. Right and the left. So here we know a little bit more about our right side. So we'll try that first, and then we'll consider the left as well. So for all values x greater than 3, we could say that's representing the limit as x approaches 3 from the positive end. So that's the limit I want to evaluate, and I'll evaluate that with the 2x squared plus 3 function. That would be all values greater than 3. So if I evaluate this limit, we'll find this limit to be 2 times 3 squared, and then plus 3. And I believe that would simplify down to 21. So we know the left-sided limit there has to be equal to 21. So, excuse me, on the right side, I believe this is left, but on the right side, our right-sided limit is 21. So let's consider what we would do for the left side. So the limit as x approaches 3 from the negative end of the graph, that would be on the left. We're going to be using the second portion of our piecewise function, that would be 4ax. Well, for right now, we could evaluate that and say that's going to be 4a times 3, and that would be 12a. Well, for us to have a continuous function at this point, our limit has to exist first. And so we know that 21 and 12 times a would have to be equal to each other if this function would have be continuous at x equals 3. So let's put these together. I would know that 12a needs to be equal to 21 for that to be true. And so we could say that a is going to be equal to 21 over 12, or we can simplify that as 7 over 4. So 7/4, or if you would prefer a decimal, you could write that as 1.75. So this is the a value that's going to force our limit to exist. And if we look a little closer, this is also going to determine our functional value. So our functional value at 3 is determined by that first line, because that's where x is equal to 3 as well. And so if I looked at my functional value, just to double check that, f of 3, we'd be evaluating this at 4 times, this would be 7/4, and then times 3. So our a value is 7/4, and our x value is 3. If we go to evaluate that, that is also going to come out as 21, which again is our limit value. So the value, the constant a is going to be 7/4 or 1.75. That'll force our limit and our functional value to be equal at 21. So our solution here would be that a value. So we can say 7/4 is going to be our solution. All right. So now we're to the stage where we're going to get to consider a number of different techniques for algebraic limits. We've already seen kind of a few arise. So we'll kind of work these kind of in pairs. So a and b are limits that we can actually evaluate directly. And these would be functions that we are continuous at the point we're taking the limit at. So if I look at part A, if I take the limit as x approaches 2 of the function 7 minus 3x squared, we'll notice that this function here is just a parabola function. And so it's going to be continuous over all real numbers, x equals 2 included. And so there's nothing interesting or funny happening with x equals 2 on this function. We're defined, and our limit's going to be exactly what our defined value is. So here we can actually evaluate our limit straight up as 7 minus 3 times 2 squared. This is not going to create an undefined value here. We're going to be continuous, and so we can evaluate that limit. So here we'd have 7 minus 12, so that would be negative 5. So that would be our limit value. In a similar fashion, part B, the function that we have is also continuous at negative 2 in part B. And so in this one, we can also evaluate this function at negative 2 and not worry about being undefined. We still are going to come out with a positive value as long as the square root contains a positive value. We are going to be defined. So in this case, we have the square root of 16 plus 5, or that would be the square root of 21. We'll just leave it like that. Square root of 21 for that value. In the next few parts, we'll have to use a little bit more work to consider parts C and D. We'll kind of do these together as well as a pair. If I considered the same method of just evaluating my function here at the limit value, here we have the limit as x approaches negative 2, we'll notice that the denominator here will actually produce a 0 when we input the value of negative 2. You can kind of pause the video if you'd like and double check that, but we will produce a negative or a 0 value in the denominator, making it undefined. So here's where we need to use kind of an algebraic technique of factoring again to consider if we can actually evaluate this limit. So here I can rewrite my limit as x goes to, or w goes to negative 2. We have w minus plus 2, and then divide by, if I consider factoring the denominator, looks like I'll have w plus 2 as one factor, and w minus 8 as another factor at work. So again, as long as we're keeping with this limit form, we can cancel those factors out and complete this process. So cancel the w plus 2's out and then rewrite our limit. That would be 1 over w minus 8. And now we're free to actually evaluate our limit at w equals negative 2. And so that would be 1 divided by negative 2 minus 8, or negative 1 over 10. So that would be our limit value right there, negative 1 over 10. The part D is another example where we can use a factoring technique to evaluate our limit. Again, if we notice in evaluating here at x equals 5, this again produces a 0, making this function undefined. And so we can consider a factoring technique, taking the limit as x goes to 5 of, this will be x plus 7, and x minus 5 if we evaluate a factoring there. And we'll have the x minus 5 that remains in the denominator. Those two factors can cancel. And again, we can evaluate this limit one more time. The limit as x goes to 5 of the remaining factor x plus 7. That's all that will remain. And evaluating that will give us just 5 plus 7, which is 12. So that will be a 12. So those are a couple problems with a factoring technique involved. The next pair that we will take a look at are one-sided limits. So one-sided limit technique. So let's take a look at part E first. We'll think about the one-sided limit technique and then consider a second example with it. So if I consider the limit as x approaches -1 plus to this function, what we should start to think about here is if I'm approaching this value -1 from the positive end of my graph, that means I'm going to be kind of evaluating this function at values that are just larger than -1. So if I consider going up my number lines, things that are just larger than -1 would be -0.99. And if I work down my number line, it would be values again that are just larger or less negative than -1 here. So as I'm increasing here closer and closer to -1, these are the values that I'm considering, kind of evaluating my function at. So if I consider maybe that value here, if I evaluate something very, very close to -1 but a little bit larger, if I consider evaluating that into x, let's start with that denominator. If I have x plus 1 and x is going to be -0.999, something very close to -1 but greater, this is actually going to produce in here some very small positive value in the denominator. Some very increasingly small positive value that's going to remain here. If I consider the top of this function, the numerator, if I have something very, very close to -1, I'm going to have something very approximate to -5 in that numerator, something very approximate. I'm using this approximate symbol very liberally here. But as I approach -1 there from above, we're going to have something very close to -5 in the numerator and something very small and positive in the denominator. So let's just consider this ratio here. If I have a kind of more or less a fixed negative number divided by an increasingly small positive number, well, this ratio is going to give me a negative value. And this negative value is going to be very, very large. If I put a kind of a fixed value in the numerator and have a really, really, really tiny denominator, that value, as it gets smaller and smaller in the denominator, will get larger and larger as a fraction, as a ratio. And so this is actually going to tend off towards -infinity as this limit creeps closer and closer to -1. So the smaller my denominator is for a fraction, the larger the number is. And so as that denominator gets closer and closer to 0, that whole ratio will tend off towards infinity. And since we do have a negative here, that will be the -infinity direction. Let's take a look at part F here for a second example. If I considered the limit as x goes to -6 from the negative end, again, if I consider approaching -6 from the left, what I'm really going to be evaluating this function at is values such as -6.1, -6.01, and so on as I get closer and closer to this value -6. So if I'm maybe, let's just choose this value, -6.01 to think about. And as I get closer and closer to -6, again, let's consider what's happening with this ratio. The denominator, again, is going to be a very, very small negative number. So if I'm going to be less than -6. When I add 6, I'm always going to be a little bit negative. It's going to approach 0, but I'm going to be very small negative value. So there's a small negative value approaching 0 in that denominator. And then if I consider the numerator, if we're approaching -6, this looks like we're going to be approaching, well, -6 squared plus 5. And again, the value here doesn't necessarily matter, but the sign does. Looks like approaching about 42, or 41, excuse me, on that side. So there would be kind of a positive number sitting here if we're approaching -6. Again, we're going to be approaching about 41 in that numerator. But again, the only thing that really matters is we have a positive value in the numerator, and we're going to have a very small negative value in the denominator. So as that denominator gets very, very, very small, this whole ratio is going to be getting larger as that's happening, and it's going to be becoming negative because we do have a negative quantity and a positive quantity, which makes us a negative value. So this is also going to be going off to negative infinity in this case, because we have a ratio of a positive to a negative, and that ratio here is going to be getting increasingly large. The last few examples are based on limits at infinity, so we will wrap up our lesson with those, part G and H. So if I take a look at the limits at infinity as x goes to infinity, we have a rational function here. And if we consider the kind of the polynomials that make up this rational function, we have a quadratic function with a power 2, and then we have a 4th degree polynomial with a leading power or degree of 4 here in the denominator. So if we think for just a moment, which one of these is growing faster? Is it going to be the quadratic or the 4th degree polynomial individually? Well, hopefully you'd say the 4th degree is growing faster. At least out of those two functions. And so if our denominator here is growing at a faster rate, it's going to be overpowering the size of our numerator. As we approach infinity here, that end behavior is going to approach 0. So this limit, actually, we don't have to use approximations. This is just going to go off towards 0. The denominator power is getting larger and larger at a faster rate than the numerator is growing, and so this ratio again is going to be tending off towards 0. It's going to get smaller and smaller and smaller, and the limit there would go towards 0. So again, all I'm kind of looking for in these limits at infinity, we'll see, is the leading powers here. In this case, it was 2 to 4. If we look at part H, we'll notice that these leading powers, when we go for limit as x approaches negative infinity, we have a power of leading x cubed and another x cubed power in the denominator. And so if I highlight those two, notice that here, both of those powers are going to be growing at the same rate, but we do have different coefficients involved. One is 9 and one is 3. So we can think in these terms that the numerator is growing 3 times as fast as the denominator. 3 times as fast, because 3 times 3 is going to give you the 9. So if we consider this ratio, our end behavior to the left would be just considered as that leading ratio, which is 9 to 3. In other words, we call that just 3. So if we looked at this on a graph, that end behavior, or the horizontal asymptote, is going to be at y equals 3 on that function. So 3 would be our limit value there. And just as a bonus, a third case you might see with these limit values, we'll just jot down here, if we take the limit as x goes to 0, or x goes to infinity, of, we'll call a function 4 x cubed minus 7x, and then divide by x squared plus 6. If we looked at this type of function here, we'll notice that the powers in the numerator outnumber the power in the denominator and that leading term. And so since the numerator is growing faster, we would consider this rational function to increase without bound, and so this will actually tend off towards positive infinity. So this will go to positive infinity for that limit value. So that would be kind of a third case where our numerator grows faster than that denominator function. All right. And that is a completion of our continuity and algebraic limits lectures. Thanks for sticking with us. Feel free to take a look at any of these problems one more time. Look forward to looking at the derivative in our next lecture. Thanks for watching.